look at standard deviation. So standard deviation, this is our formula here, which is an odd-looking formula, so we'll try to make sense of it, that the standard deviation is equal to the root of, and x1 represents just the first set of data, so this could be our x1, our number 9. Subtracted by x bar is the mean, so we're going to actually have to find out the mean of all of this data. And then when we find the difference between those two values, we square it, and then whatever that number is, we do the same process with the next set of data. So this being x2, subtract the mean. I'm going to write it in there. We square that number, and then we add it all the way up to the very last term. They use the number n because it depends on how many pieces of information there are. Then you divide it by n, subtract 1. So we have to figure out n, how many numbers there are. So I guess the first thing we can do, it's not something you have to do, we'll quickly label things. This could be my x1, x2, x3, 4, and this way we've kind of counted it too, right? 5, 6, 7,
The formula
8.
was, I think, wasn't as extensive
as this, and the process will show you how it works. This is the mathematical way to write it, but the process will actually look a lot nicer probably if we set it up almost like a chart when we set it up. The first thing we're going to have to do is figure out the mean of this, okay? So I'll quickly put these numbers in here. Let's see if I can do this. 9 plus 8. Oh, that was an awesome. Oh, that doesn't work there, so I'll have to do it here. 9 plus 8 plus 10 plus 12. And want to read them to me? That way I don't have to look up.
plus 20,
okay.
plus 16,
Perfect.
plus 17,
okay.
plus 11.
Beautiful. Okay, so all of this, and we're going to divide by the number of terms, and we figured out there were 9 terms. So our mean is 13.1 repeated. Okay, so that works out good. We have a mean. Okay, and I'll just write on by 13.1 repeated. So what we can do is we can kind of just list our chart here. We can list all of our values very quickly, and it's usually helpful if we try to put it in order from smallest to largest. The smallest term would be 8, then 9, then 10. I don't think I duplicated anything, which kind of helps out. Did we have an 11? Yeah, we have an 11, we have a 12, okay, so 11, 12, and then 15, 16, 17, 17, and then 17 and 20. Great, our 9 pieces of information. Whoops, 20. So these were kind of just chosen at random, these numbers. And our x bar is our 13.1. So it's the same number all the way through. And you can write it over and over and over again. The next thing would be
do you have to put the dash on top?
What that does is it denotes it telling it that it's the mean. This is the average.
I'm talking about the
there. We could round it, and you could round it to 13.1. I just put the dash on there to show that it's a repeating decimal, right? That's a repeating decimal forever. It's not imperative, because if we were to round that number, the number before it is 1, and it would round down, so it would just still be 13.1. Okay. So the next step on our chart here is to find the difference between the two. So essentially what we're going to do is kind of just subtract our way through this.
Right. It's getting back to me now.
Yeah. So we subtract all of these. So maybe you can help me out with the calculator. I'll start the first one. You want to start the second one, so we go through this process a little quicker. Okay. When I do 8 subtract, and we'll just do 13.1 for our argument's sake here. So I get negative 5.1. So this number is negative 5.1.
Negative 4.1. Oh yeah, I remember this.
And the process,
pattern, right?
yeah, it sometimes is a pattern. It depends how nice the numbers are. Like I used whole numbers, so they're really nice. So we can quickly tell we're gonna get 3.1, 2.1, negative 1.1. 15 will be a little different. Right. 15 subtract 13.1. Perfect. 1.9. So we get positive 1.9. This will be 2.9, 3.9, and that's another 3, so probably 6.9, but you want to double check. 6.9. Perfect. Okay, so those are all our values. The next thing would be take all of these numbers. So the way they show it is x minus x bar squared. And all we're really doing is taking these values here and squaring them, and that's what this is going to be. Okay, so we know they're all going to be positive, because even if you have a negative times a negative, you're still going to get a positive value. So for instance, 5.1, there we go, power of 2. is 2601. So why don't you do every other one so we can kind of get through this fast also. So 2601.
The next one is 16.1.
Perfect. 16.1. This will probably be 901. I get the feeling.
9.61.
Oh, 9.61?
Yeah.
Okay. 9.61. Good.
4.41.
1.41.
1.21.
21. Great. And then with 1.9.
3.61.
Okay.
8.41.
0.41. Mm-hmm.
15.21. And 47.61.
Oh, 47.61. Okay, great. So 47.61. Okay, now, according to this formula up here, which kind of looks funny, the step we haven't done yet, so we've done all of this here. We've done that part, the minus the mean squared. What we didn't do, or what we haven't done yet, is add all these values together. So that's going to be the next step here. We're essentially adding every term together. So let's get a calculator out. And a lot of times they don't do that on the side. They'll just kind of put a bar down here where we're kind of finding the sum of everything. So you want to try typing that in a calculator real quick and see if we can get everything. So the sum of all of this. Oh, sorry, did I go too quick there? Nine here.
132.09.
132.09. Perfect. Okay, so this is the sum of everything. The sum of everything is on top. We still need to divide it by n minus 1. So n is the number of terms there were, how much data. How much data do we have in this case? 9. Great. So we're going to be taking n minus 1. So you can kind of just write that on the side, n minus 1. Well, we had 9 pieces of data. Whoops, subtract 1. So that's obviously going to be 8. Subtract 1. That gives us 8. So we take this data here, 132.09 divided by 8. Okay, and we also need to square root it in order to find the standard deviation, which is usually represented with our theta here. So I can quickly put this in a calculator again. So we get 132.09 divided by 8. Okay, so that gives us a term. I'll square root, and luckily here I can just hit the number from before. So
right, and you always divide it first, right?
Yeah, always divide it first. Make sure you divide it first. And we get 4.063. So 4.063. And again, you could round to make things nicer for you. It depends how strict your teacher wants you to be with it. But let's say I did round. Let's say, approximately 4. Okay, that makes it really easy for me to set up my normal distribution curve. So I'm going to do a very quick one, just a rough sketch over here. We discovered that the mean was, right here, was 13.1, right? So a standard deviation is 4. So we need to add 4 to that number, okay, for one standard deviation. And if I add 4 to that, it's actually going to be 17.1. And if we take 4 away, it should be 9.7, I think. Right? Check. It might be 8.7. Yeah, I think it's 8, actually.
Minus 4, right?
Yeah, minus 4.
9.1.
Oh, okay, good. Oh, silly me. Okay, good. 9.1?
Yes.
Great, 9.1. I keep writing 4. Okay, so if we have our 9.1 and 17.1, what that says is 68% of our data from above should fall within there. And if we quickly take a look, that's almost all of our data. 9 is technically just outside of that, and so is 8. But 10 was within there, 12 was within there, 15, 16, 11, and was it all the way 17.1? So that. So if we quickly, I'm going to test this. Now it's a really small sample, so it's not always extremely accurate. And we did make these numbers up. But there's 1, 2, 3, 4, 5, 6. 6 of our 9 pieces of data fell in there. So I'm going to quickly do a percentage. 6 divided by 9. Let's find out what percent that is. How close are we to our 68%?
0.66.
There you go, 0.6 repeated, which is roughly 67, so approximately 67. That's really close to our 68, so that worked out really nice. Our second deviation, so we'd add 4 again. So 4 and 17 is going to give us 21.1, so that's 2 deviations away. And if we subtract 4, that should give us 5.1. 95% of our data should fall in there.
We don't have to multiply it by anything?
We could. What I did instead is I just, let's see what right here. What I did is I just went plus 4. So I brought this over, plus 4.
Right.
And then I can just plus 4 again from that last term. It's the exact same idea as going from the mean, multiplying this by 2, and adding it. Okay? And then you could do the same one for the third. You can just add 4 again, and it'll take you to your third
Can you do that
deviation.
every time or just
Every single time. And you can do the same process here. We subtract the 4, and you have to subtract by the deviation. Then I just subtract it by 4 again. It's the exact same thing. You'll always get the exact same number. And finally, for our third deviation, you can just subtract 4 again. So this number would be 1.1, and this one would be 25.1. And sometimes that's a much faster way to do it than to actually multiply, right? If we look above, between 5 and 21, that was all of our data. Every piece of our data, let's do yellow here, fell within there. So for us, it wasn't 95%. It actually happened to be 100% of our data fell in there. And that's because we had a really small sample size with what we're doing.